All right, let's just dive right into this explainer. Today we're tracing a pretty fascinating journey, going from intuitive physical guesses all the way to mapping out precise boundaries. We're going to unpack the educational roadmap of Chapter 6, Measuring Length. You know, we take measuring for granted every single day, but it's actually built on a really carefully designed progression of ideas. It's not just, slapping numbers on a ruler. It's about how we fundamentally make sense of the physical space around us.
So, to ground this, the text anchors everything to a super relatable, real-world experience, kids measuring their own height. You've got one child carefully holding the tape measure for another, and this instantly answers that crucial question. Why does learning to measure actually matter in the real world? Because let's be honest, before we ever care about abstract math, we care about ourselves, right? Am I getting taller? Can I finally reach that top shelf? That innate human curiosity is basically the perfect launching pad for scientific precision.
Here's our roadmap for the explainer. First, the language of length. Second, measuring with ropes. Third, the need for centimeters. Fourth, meters for the big stuff. And finally, discovering the perimeter.
Part 1. The language of length. Translating our world. Now, think about this. Whether we describe a door as tall, a desk as wide, or a pool as deep, all of these words fundamentally roll up into one ultimate concept, which is length. The source material points out that we toss around these different terms purely based on orientation and context. But mathematically speaking, it's all just distance. It's all length. And recognizing that honestly simplifies the physical world beautifully.
Moving on to Part 2, Measuring with Ropes. Building an intuitive grasp. The text brings in these brightly colored ropes to use as tactile, hands-on tools. Students can actually walk, jump, or crawl along the lines. Think about that for a second. Instead of just staring at a whiteboard, they are physically creating 1 meter, 5 meter, and 10 meter lines right on the ground. They literally feel how big a distance is before ever attaching standard numbers to it. It's a brilliant way to let the body teach the brain.
Then, the chapter does something really clever. It asks learners to take a 1 meter rope and actually fold it in half, to visually see what half a meter looks like. Then they fold it again to get a 1/4 meter. This masterfully bridges the gap between whole distances and fractions. You're not just memorizing that 2 halves make a whole, you're literally holding that reality in your own 2 hands.
And the text constantly keeps you on your toes with active prompts. It asks you to estimate the length of a jump, or maybe guess the dimensions of the classroom first, and then contrast that guess with an actual measurement. This forces a major cognitive leap. Guessing a distance and then verifying it with a rope trains your brain to calibrate its internal estimation engine. You quickly learn just how accurate, or wildly inaccurate, your own eyes really are.
Part 3. The need for centimeters. Scaling down for precision.
So look at how an intuitive, non-formal unit, like an outline of a hand, naturally reveals its own limitations. Because, well, if I measure a desk with my hand span, and a child measures the exact same desk with theirs, we're going to get completely different numbers. This visual bridge perfectly illustrates exactly why we need a standardized measuring tape. We need a scale that stays identical no matter who happens to be using it. From there, the chapter lists out these tiny, everyday objects to spark a bit of a realization. We're talking an ant, a grain of wheat, a rajma seed, an eraser, a fingernail. If all you have is a big 1 meter rope, it's totally useless for measuring a grain of wheat, right? It's way too big. And that creates the absolute perfect logical setup to introduce the centimeter. We desperately need a unit that is scaled down to measure the tiny marvels of our world.
Part 4. Measures for the big stuff. Measuring the giants. And right here is the absolute vital mathematical anchor of the whole chapter. 1 meter equals 100 centimeters. It's a great reminder that a standard meter scale is really just that little 1 centimeter bar repeated 100 times over. Suddenly, the massive scale and the tiny scale are perfectly logically linked together in a system of hundreds.
Now, to keep the pacing really energetic and light, the text throws these wonderfully absurd estimation questions at us. For instance, it notes that a single blue whale is about 6 meters long, and then asks you to figure out how many buses that would equal. By forcing you to compare a giant ocean mammal to a massive city vehicle, your brain gets an incredible workout in spatial estimation.
The fun absolutely continues when the chapter prompts us to imagine stacking 2 ostriches, yes, ostriches, one above the other to calculate their combined height. It turns math into this vibrant, playful mental puzzle. It proves that practicing addition and wrapping your head around large-scale height doesn't have to be dry at all. It can be as wildly imaginative as picturing two giant birds balancing on top of each other.
Finally, Part 5, Discovering the Perimeter, Defining the Boundaries.
We hit this precise definition of perimeter, which shows exactly how all those concepts of height, width, and standard units culminate into one big idea: the ability to measure the exact boundary of a closed figure. We've officially leveled up. We aren't just measuring a straight line anymore. We are tracing the entire outline of a shape to figure out its total outer edge.
Now, while the text totally acknowledges that you could use thumbprints or block prints to kind of estimate a boundary just for fun, it really emphasizes that graduating to formal tools yields true accuracy. Like, if you were building a fence for a garden, which is actually one of the examples the text mentions, a rough estimation just won't cut it. You absolutely need a formal tape measure to know exactly what you're dealing with.
And look at how this translates into a brilliant practical exercise. Using a visual grid, the chapter ensures learners aren't just blindly memorizing formulas. Instead, they look at a 1 centimeter dot grid, physically trace the boundary of a completely irregular shape, and count the units one by one. By visually mapping out these 1 centimeter chunks to calculate the perimeter, students deeply internalize what perimeter actually means in real physical space.
It really is an amazing journey, going from simply guessing how far you can jump on the playground all the way to calculating the exact boundaries of complex geometric shapes. So as we wrap up this explainer, I want to leave you with a thought to take into your everyday life. This chapter starts with footsteps and it ends with perimeter. What unmeasured boundaries in your own world are just waiting to be explored today? Go grab a tape measure and start looking.